So welcome to the continuing 2024 webinar series for the multi-sector dynamics community of practice. Today is advancing MSD research with artificial intelligence, and this is the debut of our AI working group. For our webinars, please be considerate, respectful, and collaborative. Keep muted unless a facilitator calls on you to speak. Maintain a supportive and positive environment and respect any questions or input from other participants. Today's agenda, I'll give a brief introduction to the multi-sector dynamics community of practice. Then there'll be the AI and MSD working group presentation from Stefano. Then there's three guest panelists, Andrea Castelletti, Chaopeng Shin, and Nicole Jackson. And then there'll be a panel discussion. And after that, the working group will be eliciting your feedback in some interactive Google Doc exercises. So in short, what is MSD? We're looking at studying the complex built natural and socioeconomic systems that co-evolve in response to change, as you can see illustrated here, with a particular interest in human Earth system feedbacks and how they shape the interdependent pathways of societal change. So we have been working to create a community of practice. And the idea here is to accelerate the development of needed foundational capabilities in the science through open science and growing a diverse transdisciplinary workforce. And our working groups are a critical component of that. And the AI working group is something that was pretty central to our vision. And so if you haven't had the opportunity, we have the current report that was released January 2022. You can see here. And as you'll see today, the AI was actually a pretty central focus in some of our gaps and research needs. There's also a new Earth's Future special issue, so consider yourself invited to contribute. I'm not going to read off all of my co-organizers, but you can see it's a broad group, and the focus is on advancing complex adaptive human Earth system science in a world of interconnected risks. We have a fairly broad window, so it should be feasible to contribute, and that's open through December 2024. I am the lead editor for this, and so if you have questions or are wondering if your work ties into this, feel free to reach out to me, Patrick Reed at Cornell University. And with that, I would encourage you to visit the Multi-Sector Dynamics website. And if you're not signed up for our newsletters or our working groups, you can join us here. So with this, I'm going to stop share and then pass to Stefano.
All right. Right, I believe you can all see my screen, right? So good morning, afternoon, or evening, depending on where you are. I guess first question is, why do we need a working group in AI? But mention something about that. So the next 3-4 minutes, I'm going to go a little bit deeper into that before introducing the speakers. So back exactly to what Pat was showing just a few slides, before, the research vision for the multi-sector dynamics identified a few important areas that are strongly or actually centrally related to AI. So first of all, opportunities in the sense that there are major advances in algorithms and HPC systems that could be leveraged. Challenges, of course, because several MSD applications combine multiple models, so the complexity of these applications goes often beyond what we have been used to see in some application areas, for example, in machine learning. And finally, there's a community need as well, in the sense that scientists in the MSD community should work more closely with folks in computer science, statistics, etc., more broadly in the area of artificial intelligence. Now, this is perhaps more of a top-down view. There was also strong bottom-up demand for this, for a working group in AI. At the MSD workshop in Davis last October in 2023, we discussed about creating this working group. So what I'm showing here are a few quotes that I believe are particularly relevant. And perhaps the most relevant one is need for overall education, with focus on what is happening in emerging areas in AI, as well as the need of using AI tools to capture multi-sector interactions or better understand our models. So looking at these different needs, we thought about focusing on 4 main areas for when it comes to this working group. And in particular, the questions that we have is how can we use artificial intelligence naturally within the domain of multi-sector dynamics to expand the breadth and the depth of data that are available as we develop models or more broadly for our applications? How can we use AI to understand our model structures? And the bottom line here is that in MSD applications, several models become extremely complex to the point in which AI could perhaps help us understand what is happening within our models. Third point, using AI for model diagnostics of complex model chains. And finally, using AI or expand essentially the tools that we currently have to plan and control large systems. For example, when we have interconnected infrastructure systems that require complex control algorithms. Now, a caveat here is that these are focus areas that we think are relevant. Naturally, this doesn't encompass the entire spectrum of different elements that AI could be leveraged and used for multi-sector dynamics. But again, this is what we believe could be relevant. And later on in today's webinar, there will be opportunities to give us a feedback and see whether perhaps we could steer this a little. And these 4 areas are also strongly related to the 3 speakers that we have that we've invited for today. So Professor Castelletti is leading from Politecnico di Milano, is leading a major project funded by the European Union on using artificial intelligence to have a better understanding of extreme hydroclimatic events. Professor Shan from Penn State is a leading figure in the domain of artificial intelligence, machine learning, and hydrology. And Nicole Jackson from Sandia National Labs is an expert in the domain of coupled water and energy systems. So without further ado, I will stop here for the moment and leave it to Professor Castelletti. Thank you.
Thank you, Stefano. Thank you, Pat, for inviting me to this workshop. So my presentation, as Stefano mentioned before, will be about using artificial intelligence to study extreme climate events. This is part of a large project I will tell you something about later. So we know changing climate is causing extreme events to become more frequent and more extreme. So drought, heat wave, cyclones, hurricanes, or tropical cyclone, depending on where you are, and floods as well. And of course, these also mean more cost because, for example, over the past 40 years, extreme events brought damage close to 150 billion per year, of which 15 in Europe and 60 in the US, not to speak about the death toll. And this is a sector where artificial intelligence is increasingly being used. This is just to mention a few new initiatives. There are a number of projects and initiatives going on in Europe. CLINT is the project, Climate Intelligence. We are leading. There's a twin project, XIDA, which is another large, more than 6 million project. But there are also other initiatives internationally. There's this community called Climate Change AI. There are donors like Bezos, Earth Funds, and Leonardo DiCaprio, which are funding exactly application of artificial intelligence. And more recently, also a couple of new journals, one as part of AGU, Xiaopeng is one of the editor, a second one called Environmental Data Science, where again, in the editorial board, there is a large number of AI experts with application in the climate and earth science domain. And again, suppose many of you have been involved in recent AGU and EGU conference and initiative, and probably surprised by the huge number of sessions and participants contributing with AI application. What you see here, for example, is recent search in Google Scholar with keywords machine learning and climate science. So you see how many applications per year. Now, the question is exactly how artificial intelligence can be used for climate science. And so try to summarize a number of challenges and way of approaching this challenge. Starting from data, one peculiarity of extreme events is that by definition they are extreme, and as a consequence, there's no many occurrence of them in observational data. So a big issue with this data is data scarcity. And the second thing I want to mention is that most of these extreme events have a kind of image-like representation, so they have a spatial heterogeneity, so they can easily model using image processing type of AI tools. So I was mentioning extreme events are rare events, so there are not so many data where we need many of them if we want to use artificial intelligence for other applications. So data, synthetic data generation, data augmentation is one of the main challenge and application for which generative AI can be used. So diffusion model, but also GANs model can be basically used for this type of purpose. Just to mention numbers, category 5 hurricanes occurrence are very, very limited. So we just mentioned few of them per year. So this actually means that we need a generation of data. Then second challenge, again, in the realm of data, is related to bias in data, mostly coming from reanalysis data, so model output, and not just observational data. And again, machine learning and artificial intelligence can provide quite strong support in unbiasing this type of data. Here, type of methods adopted are generally UNet, so convolutional type of neural network. And you see here example of unbiasing extreme precipitation connected with tropical cyclone. The third problem is related to gap in data, so missing values. Again, this is something which is somehow structural for extreme events because observational monitoring networks are quite sparse globally. So if you want to have a global data set, we need somehow to fill in missing data, both spatially and temporally. And so again, here, generative models like diffusion model and generative adversarial neural networks are solution, as well as convolutional neural network can be used quite successfully. Again, you see an example from some of our application. And then moving from what I would call data preprocessing, there are few but very important application domain for extreme event. One is related to detection, so detecting when extreme events happen, and second, understanding which are the main drivers of extreme events. And here is where, in my opinion, artificial intelligence is really contributing the most, because most of the extreme events are described by very simple empirical index, like I don't know, cyclone generation index, which are somehow combining few variables in limited spatial domain through very empirical type of mathematical laws. And with artificial intelligence, what we can do is starting from scratch from original variables sparsely distributed across all the globe, using and exploring also teleconnection with different time lag. And so trying to discover a new type of index, new type of drivers and relationship. And again, this can be done in 2 dimension, in 3 dimension, using image processing AI. And next step after detection is attribution, which is somehow related to detection, but the focus is on finding anthropogenic drivers causing climate change. And again, here is, I would say, a quite recent type of application by artificial intelligence. But there are many successful work proving that ensemble of neural network, for example, or autoencoders can be used to extract pattern and somehow combine this pattern to anthropogenic drivers. And then moving to more operational application of artificial intelligence for extreme event, we and many other groups are working on using AI and machine learning to do forecasts over subseasonal and seasonal scale of extreme event, for example, heat waves. But also, again, like for detection, using this type of machine learning approach for feature selection, so for the identification of drivers of these extreme events. And so once you have the drivers, you can also think of building very simple forecast model, which may be also something that is appreciated by policymaker and end user. And so you can either directly predict heat wave using machine learning or using machine learning and AI to extract drivers of extreme event and then use simple model for prediction. Finally, so last but not least, causal discovery. Now, causal discovery probably is the most recent type of application of AI for artificial intelligence, but is also one of the most promising, and maybe we can discuss this later in the panel, is one of the application where probably there is more potential for using AI and supporting through AI climate science. Here again, there are many artificial intelligence solutions being started, like PCM, CI protocol, transfer entropy. Is still really in its infancy, this type of causal discovery analysis, but is really, how to say, an important point also for the interaction and communication between artificial intelligence expert and climate scientists. Now, why this is relevant for MSD? This is relevant because in this project, which is called Climate Intelligence, we've been trying to combine artificial intelligence with impact model. So the idea is a large project involving 15 partners across Europe from 9 countries, and both climate scientists, artificial intelligence experts, and impact modelers. So what we do, we are focusing on different types of extremes, so cyclones, hurricanes, drought, heat wave, and then compound and concurrent extreme event. And we are exploring a number of challenges, basically all the challenges that I mentioned before. But what we're doing here is that instead of looking at the value of artificial intelligence in terms of improved accuracy in all these tasks, we look at the value as measured by the impact model in terms of multiple sectors, so water, energy, food, ecosystem, and other sectors. So the idea is we take a traditional approach from climate science for forecast, for example. We developed the AI-enhanced forecast, and then we measure the value of AI enhancement in terms of improvement in performance across different sectors. So, for example, how much more energy can be produced if we operate the hydropower using AI-enhanced forecast with respect to traditional forecast, how much more food production can be ensured using seasonal forecast produced through AI with respect to traditional forecast. We are working at the continental scale, so it's a work that we're doing across scale. So we're looking at the continental European scale, and then we selected climate change hotspot, delta system, alpine system, arid area, semi-arid region. And for example, Zambezi is one of the climate hotspots we consider. Here we have both extreme drought that cause sometimes even switching off of large hydropower system, and of course tropical cyclone. I guess the last one was Freddy, you will remember recently, mostly hitting the Delta area and the Mozambique region. There are plans for expanding hydropower, for expanding food production capability, but of course all these extremes are challenging the investment and making them more risky. So what we're doing here is exactly developing the work pipeline that I showed you before, from data processing, detection, forecast, And then we use this information to inform an operational model, which is used for both studying operation of existing infrastructure and studying adaptive planning, strategic planning of future expansion in the basin. So with this, I want to thank all the people involved in this work on an extreme event, particularly Guido, who is leading scientifically our effort in clean. And that's it. If you jump on our website, you can also find a link to the Climate Intelligence Project and additional information. Thank you.
Thank you very much, Andrea. So our next speaker is Professor Xiaopeng Shan from UPenn. Xiaopeng, I think you can just go ahead and share your screen.
Sure.
Thank you.
Hi, everyone. Nice to be here, and thanks to the host for the opportunity. Yeah, this is Xiaopeng Shan from Penn State, and we do publish our code here on this website. So if you're interested, please check out. And there's a new journal on JGR machine learning computation that you can submit to. And also check out hydroml.org for the Big Data Machine Learning Hydrology Symposium. Okay, so in this talk, I would like to share some of our work that is using machine learning and physics-informed machine learning in the domain of water and hydrology. So many of you are maybe quite familiar. In the domain of water, the deep learning has been introduced for quite some time now in hydrology, right? And the neural network that has become very widely adopted is this long short-term memory. And in this network, it's a time series model. It learns to retain information longer and then discard some of the other information. And a very typical way this model is set up is that you have some forcing and some attributes that get sent into this LSTM, that it predicts something else. You get to train it, and you get the meaning of soil moisture, streamflow, water quantity, et cetera, right? So this first paper was actually in 2017, and a typical figure you see here is that the blue curve, which is the LSTM model, can go through the data points, which are these red circles, almost completely in this top performing pixel, but it's missing some of the peaks for a medium performing pixel. And and every pixel you have a prediction, and you can calculate the correlation. And over the United States, you have a correlation mostly above 0.9. And later on, a lot of other people in the community started working on rainfall runoff modeling. And this is also another figure that you see a lot, which is the CDF of the NSE. Nash-Stock efficiency coefficient. If you're unfamiliar with that, you can kind of think of it as R squared. So the blue line here, curve toward the right is a better model. So the blue line here, the black line here represent the traditional model. The blue line represent a LSTM model, and the difference between the median is from 0.64 to 0.74. It is really a big change, and that leads to somebody to say in the community to say that this is a step change in our predictive capability. So apparently it's doing something right, and our previous model was missing something else. And interestingly, you can also do data assimilation very easily with neural networks in different ways. And they give you this red curve, which has a median NSE of about 0.86 over 500 basins over the United States. Now you can also do the same with the transformers. And we recently get a paper. The thing is, the transformers don't seem to actually show a lot of advantages in terms of the time series prediction compared to LSTM if you actually rigorously or apply it on this benchmark data set. However, we think that this time series machine learning, there's a lot of papers in each year now, but we think it's still not entirely satisfactory because we do not know, we do not understand this model. When we go directly from X to Y, they probably lump 20 different processes inside, and we do not fully understand it. And we cannot test a specific hypothesis. We cannot ask a specific question. So we then start to ask the question, what if we can absorb the genes of AI, the kind of the thing that works very well for them, the wonderful ideas, in this case, the ability to automatically learn from data and from a lot of data. What if we can absorb that genes of AI into our domain without taking its full form? So we started to proposing this idea of differentiable modeling in recent years, and this represent a seamless coupling between neural networks and process-based equations, which we call priors, right? Because they're not trained. And the neural networks are essentially question mark that you can insert anywhere in the system. So now from X to Y, we say that there might be 8 different parts of the model, and you say, I believe 6 of these different parts, but I don't believe G1 and G3 as 2 parts of the model. So you can throw them out. You can replace them with neural networks. And what is demonstrated here is that we can train this whole thing, these neural networks, together with the process-based models on big data, right? So we can get the best part of the machine learning, as well as some of the physical priors that brings its own benefits, right? So the priors, they serve to constrain the learning to an interpretable scope. So you know what, a typical thing you see is here, where you have a neural network and you have the attributes and forcings, and this neural network can output actually static or dynamic parameters, physical parameters, to serve the physically busted model. So this model uses these parameters to make a prediction that this other prediction is compared with observations, and we back propagate to indirectly supervise this neural network. So we don't have the ground truth for the direct output of this neural network, right? But they can work together as long as the model is what we call differentiable, meaning that they can produce gradients very quickly. So why is the DM very transformative? Because it learns universal laws from big data, and I will show you results from that. And so it has very high performance, and it maintains physical concepts at the same time. So we compare these uncalibrated or untrained variables with observations, and we find that the ET in space and or in time compare very well with MODIS-based estimates, also base flow, with base flow separation techniques. We also compared like soil moisture with other observations. Actually, somebody else did this comparison, and it also compares. So that means these variables that are not trained directly also maintain their physical meaning. So now you can use them to make physical narratives, right? They're interpretable, and you can use them to tell the story. And we also show that it has very robust spatial extrapolation. In fact, these differentiable models do better than LSTM in a data scarce setting, which is not surprising. So we actually underwent many iterations, and some of these curves you see here. The black curve is a popular LSTM version in the community called the Krazis version. The green and orange line are the HydroDL. That's our version of the LSTM. That's kind of slightly to the right, almost kind of indistinguishable. Okay, but you see this dashed line here is a newer version of our differentiable HBV that overlaps almost entirely with the state-of-the-art LSTM model. So you get the best performance. In order to get this, we actually employed like an adjoint method that allowed us to solve implicit equations that gives us the high numerical accuracies that solve the last bit of that difference. So you get the best performance, but also physical interpretability. Okay. We can use a DM to learn unknown relationships. For example, these parameters can be a function of catchment area, and this response, this scaling function, is always something that we've been looking for, right? So based on this learning, we can see that the mean water supply would actually in the arid region would first decline until around 50 kilometer scale, and then it stabilizes from there, and it actually kind of recover a little bit. And this is due to groundwater return flow playing a more important role at this length scale in arid regions. In the humid regions, they actually reached this balance far earlier. Okay, and we see that the groundwater ratio is becoming larger and larger as we go downstream from left to the right as you going downstream. So all this kind of understanding can be obtained by placing the neural network where you have a question and learn a relationship there. And we also this is also widely applicable. You can apply it in biogeosciences. And this is based on photosynthesis model where neural networks is predicting the parameters such as VC max 25 or moisture constraint parameter that is then sent to a physically based photosynthesis model. And then we actually can compare this with multiple observations and constrain the system. We can learn how vegetation is climbing to the environment in the different parts. And this actually ends up giving you a large difference between the different model variations that do not account for this climation. We are now using this differentiable hydrologic model as a candidate model for the next generation national water model. As you can see, this is the previously published result on the lower end. The upper panel, you can see there were pushing points toward the upper left here. And and we're pushing points from this bar to this bar to this bar. That's why you see this bar is taller than that one, because we're improving the performance overall. And overall, we actually can sort of beat LSTM on this very large data set. And this is a very high performance because previously you get to be 0.67, right? Lastly, another gene of AI that you can borrow is like generative modeling. And we can build, for generative modeling, we can capture the coevolution and the joint distribution of physical parameters in the environment. For example, we train this joint distribution, this well, we call it ChatGPT, but you can call it whatever, right? We use it to predict these constant, these physical quantities, and we find that it does a much better job than random forest or LSTM. But what it means is it can capture the joint evolution of things under change. With that, I would like to summarize. So the data-driven model, we can use it as a scout, but differentiable model can be used as an army to really study a problem and understand it with, again, insights and ask questions. And we're also entering the age of mega AIs for the environment by these generative models. With that, I just end it here.
Thank you very much, Xiaopeng. So I'm happy to introduce our third and last speaker. So Dr. Nicole Jackson from Sandia Labs, please go ahead.
All right. I am hopefully sharing. All right, so thank you, Dave and Stefano, for the invitation to be here with you today. So a lot of my work focuses on the energy sector, and so over the next few moments, I'm going to kind of do a high-level overview of two sets of work that are specific to the energy sector and how we've started to use machine learning to predict impacts and understand system behavior in the context that you have an extreme event. And so before I get into the actual projects and work, I do want to thank my co-authors across Sandia, Vanderbilt, and EPRI. And one key thing that does come up in the ML space is data, and I want to thank my industry partners as well as the Department of Energy's different offices who have funded different pieces of this work over the last few years. Okay, so to motivate this work, and thinking about the context of the grid, there's a lot of co-occurrence of severe weather that happens and it results in power outages. And so here you can kind of see a snapshot of time series over the last few years of ebbs and flows of these things co-occurring. And one other thing that we have also happening at the same time is, and it's a great thing to have, is the increasing amount of renewable energy that's being brought online to the grid. And so one question to start to think about when you have this co-occurring situation of outages with extreme weather and these new types of energy generation sources is really how can we start to use these new analytical techniques like machine learning to understand what's happening with the system and how we can improve predictive modeling in the context that these events happen. And so really briefly, I did want to touch on that a lot of this is focused, my work is currently focused on the machine learning umbrella within the broader AI space, and wanted to just briefly show that there's a lot of different parts of machine learning that you can use depending on if you're focused on feature extraction, feature selection, prediction, and all kinds of things. But for today, briefly, it's focused on thinking about how can we develop accurate models, which is important for prediction, and how can we start to think about using explainable techniques to help understand things that are happening within the system. And so it all comes from a place of where do you have lots of data? And so a little bit of a contrast, although a great setup from Xiaopeng and Andrea, when you're thinking about the environmental or the climate system, is when you start to transition and thinking about critical infrastructure or the built environment, you actually do need a fair bit of system level information. And so there's a couple different flavors that comes through. You can ask people how their system is performing, you can have operations and maintenance data, and then you can have performance data in and of itself. And so you can actually start to fuse that data together to create one cohesive set that describes the system in total. But then if you're starting to transition to thinking about, well, how is my system performing in light of all these kind of ambient conditions, if you will, you start to actually think about bringing in a lot of what I refer to as external data, because it's outside of the general system. And that can be weather in the form of long-term climate series data or storm data, environmental stuff like land use, land cover information, and socioeconomic data. So you can further fuse that in with your data set. And then you can actually start to think about how you do your modeling and analysis with a goal in mind. And my particular research portfolio is largely focused on quantifying those impacts of extreme weather to critical infrastructure. And so you can do that in a statistical way, but more recently, a lot of work has been focused on bringing in some of those machine learning techniques. And so two of the stories that I'm going to really go through quickly. One is using explainability to understand low performance drivers for utility scale solar during snowstorms. And on the other hand, using machine learning to develop a predictive model of grid outages during hurricanes. And so first up is the work related to extreme weather and utility scale solar. So you can start to kind of take all of your data that's been fused together and partition it and say, well, we have an event and we don't have an event. You can do lots of statistics to help quantify those differences. And in this case, it ends up being a 55% reduction between those snow and no snow days. But really what we're focused on is, if you're thinking about that bottom part of your performance ratio, what's really driving that to be the case beyond, hey, we had snow. And so here we actually developed a very, well, it's an okay size panel. It's not as large as the second paper that you'll see, but you can have a selection of variables that span weather, operations and maintenance, and metadata that's capturing where the site is and how it's being operated. And so you can bring all that together in a very large panel and do a random forest regression. And so this one in mind was not focused on prediction. We just wanted to take all of these complex nonlinear interactions across all of the data variables and say what's happening for low performance. And so one of the things that you start out with in doing machine learning is your variable importance or feature importance plot. And so here we've kind of capped the top 6 drivers that are occurring to help explain some of the performance, and plant age and having lower radians, and cumulative snow, meaning we have snow that's constantly being added to the site. Are some of the leading things. And then if we want to actually further go on to explain, you can use, there's a lot of different techniques available now, but in this particular instance, we use the local or interpretable model agnostic explanations, or LIME for short, to further basically take the part of the panel where we know we had it classified as low performance, and then use LIME to actually understand the ranges within those variables, if they were continuous, or if it was a discrete variable, which of the options or categories within that variable were actually helping to contribute to understanding that low performance. And so, yes, you can see lower radiance is a factor, but you can also start to see with some of the net daily snowfall that when it falls within a certain range, that's also going to be a marker that you're going to have substantially low performance. And so this gives you a sense of how you can start to use machine learning to help diagnose what's happening with your system. And then if we can take it like a much larger scale and think about the grid at large, you can use machine learning to help understand system behavior across a wide area extent, like a wide area extent event like a hurricane. And so that's what we've done in the second paper. And so for that, we have a different set of variables, but it does have a very similar theme to the big flow chart from earlier, where you can start to think about your static environmental variables with land cover, DEM, your root zone. You can have dynamic weather, which is all your weather and storm information, along with some socioeconomic data. And altogether, we started out with 162 variables. So it really becomes a fairly high dimensional problem. And our 2 outcome variables in this particular case, we're thinking about how long the power outage was going to last in terms of hours, and how much of our customer base was going to be affected by the event. And so checking for multicollinearity, it ends up being reduced to 142, which is still a fairly substantial number and makes it ripe for handling. Machine learning is ripe for handling that. And so with that in mind, the first part is thinking about what happens during outage duration. And in this particular effort, we use 3 different types of machine learning based models, BART, MLR, and XGBoost. And so you can see the 3 compared to the actual time series just for the outage durations. And the XGBoost based model performed pretty well based on R-square performance metric. And similarly, we can also consider what happens with the maximum percentage of customers that are affected. Although it's not as high performing as what happens on the outage duration side, nonetheless, XGBoost is still a really good model for predictive power in this particular case. So we have two different models now that we can actually do some fun numerical experiments with that have performed pretty well based on historical conditions. And so this is just how the model performs, but similar to what happens on the utility scale solar project, how are the variables actually comparing and what's driving our ability to have a high predictive model? And so in this case, you can do a feature importance plot similarly. And for this effort, we actually did take the different classifications of variables. So if you think back a couple slides where we had our weather variables and socioeconomic and environmental, unsurprisingly, most of the models variables or performance is being driven by those weather variables on the outage duration side. And you can see something similar for what happens on hurricane impact in terms of % customers affected, although socioeconomic and environmental factors do start to have a little bit more importance. And so with that, a brief wrap up of a really, really fast way of thinking about how you can start to explain when you have a pool of generators, how you can start to explain low performance using explainable ML. And then on a larger extent in terms of thinking about the grid as a whole, you can actually start to develop predictive models based with lots and lots of different variables to both tease out how long a particular type of event is going to last and start to predict how much of your customers or people or communities may be affected by a given event. And so a lot of this work is actually based in historical conditions. And so with these efforts that we've had based on those priors, now it really opens up a lot of fun things to do because we have really good understanding under known conditions how these systems have performed. And so one thing that some collaborators and I are exploring is thinking about how we can actually turn this into an optimization problem. And there's some really cool work coming out of Sandia that's related to now you can take neural networks and actually have the optimization problem with an embedded neural network. And so that opens up a lot of fun opportunities in this space. And this work that I've presented over these last few minutes is really kind of scratching the surface on how you can start to use machine learning. There's other parts, if you think back from several slides ago, of different techniques, but there's the whole broader panacea of AI. And so there's lots of opportunities to further explore scenario generation. And then you can think about reinforcement learning can start to handle, you have an event and an agent response and how the system performs and having a really nice albeit complicated, but really nice loop that AI allows you to start to model. So with that, I will turn it back over to Stefano and Dave.
Thank you, Nicole. All right, so first of all, thanks again to the speakers. And we have roughly 15 minutes, more or less, for the Q&A part of this webinar. So I would please ask you to post your question in the chat. And before going to the audience question, we prepared just a couple of questions for our speakers. The reason being is that we would like to steer the conversation a little bit towards the main themes that you've seen today that I've introduced before as well. So one question for Andrea. It's a little bit long, Andrea, so let me just go to the to the core. So going back to what you presented, the question is, do you think that through the AI tools that you've been presenting today, is there any specific physical process in relation to climate, for example, heat waves, that we understand better, we can predict better, that we can model better, more broadly? And if yes, what are the implications for, I would say, researchers studying the impact of these extreme events on human activities / MSD research?
Yeah, thank you for the long questions, Stefano. The answer, I would say, the two things, in my opinion. One is that there is a big potential for downscaling a fine-scale process, like, for example, for hurricanes and tropical cyclone, these wind gusts, which are not so well characterized in climate models, and this would allow to also look at hyperlocal scale impacts. And so this is one thing for sure. Second thing comes to my mind is that many different type of extreme, and these apply to tropical cyclone, but also to mostly more than tropical cyclone to drought, are characterized through index, which use very general information. While many of these drought, particularly if you look at their impact, they are very, say, linked to local dynamics. So, for example, drought in a highly regulated system may be depending upon, local storages, groundwater, snowpack available, and so on and so forth. So, one of the potential of AI is to quickly and automatically build a ad hoc index, which allow you to characterize extreme events in a very customized, say, with respect to the local, to the geographical dimension way. So you can really differentiate index through AI depending on where you are and what you're looking to. And this applies to drought, in my opinion, particularly because they are very sensitive to local process and dynamics. More in general, I would say that generative AI and the potential to do this data augmentation, to literally extend massively the number of data available, would really boost the possibility of better studying many climate related process.
All right, thank you, Andrea. All right, then one more question for Xiaopeng. Again, a long question, and I'm sorry, we can only type long question, but again, to the core of the question, moving perhaps more to the domain of hydrology and water resources more broadly. This again strongly relates to what you presented, but how can AI help us understand better the underlying structure and behavior of hydrological models? And you spoke about that. But I guess the other interesting thing and the other aspect of the question is whether you think there will be, or what should be, the major next leaps in AI that we should dream for or expect that are gonna even push us forward in terms of our ability to understand and explain hydrological processes.
Yeah, thank you for the good question. I think this first question is related to the differentiable modeling that we proposed. In a way, I think there are so many uncertainties and so many unknown relationships or poorly understood relationships in a whole hydrologic modeling chain, not just in the physical processes, but also in the social domain as well, water demand and all of those things. And I think differentiable modeling helps. It's a generic framework that helps you to ask a question, right, without imposing a strong relationship for that equation. Rather, you can use neural networks to understand certain component. But if you think about it deeply, in order for us to ask a specific question with some concepts, you need the support of physical concepts, right? You say, okay, what is the relationship between A, B, and C? You must first have the concepts of A, B, and C, right? So that is typically lost in a directly supervised machine learning model, because many of the physical concepts that you need in the middle are not extensively observed, right? So in order for us to ask a question, it necessitates that we make some priors, we have some assumptions or equations that are there. And the reason that they exist is to impose a prior, and they bring forth the physical concepts, right? And that's very critically important for understanding underlying structure and behaviors. Secondly, I think I talked about briefly about I think DM will be a huge leap forward. It will bring a lot of advances, more specifically because it allows you to ask specific questions now, right? Any question you want. Now, previously you cannot do that. Now you can. However, I also showed the generative modeling. I think that's going to be a major breakthrough. It really has a practical benefit because it models the joint evolution of things, how they evolve at the same time, right? So how does ChatGPT or these graphical AIs give you a picture that seems coherent because it captures this joint distribution, right? So I think that will be a very useful evolution in the next stage. And one thing I haven't shown, I guess it's probably less relevant here for this community, might be the ability to solve partial differential equations very efficiently with the right sensitivity. In the past, it's been very computation expensive, or with the AI-based PDE solvers, they have some trouble with the sensitivities. But now there are approaches to actually solve both of these problems at the same time. So now the PDEs can be solved at much lower cost. I stop here, so that's it too much.
No, that's just great. Thank you. Okay, and then shorter question for Nicole. So as we've seen, of course, your work deals with the impact of extreme weather events and how that cascades on critical infrastructure system, for example, solar panels. So what do you think are the gaps that still exist? There's a lot that we can do now, as you've shown, with machine learning, more broadly with other AI tools as well. But there are gaps as well, right? For example, as you transition from one study to the other, especially in the second study, you were showing that there can be some challenges there, right? So more broadly, what do you think are the challenges that AI with current or with tools that are currently being developed should target in the field?
Yeah, and Chopin did a great job of highlighting understanding kind of the underlying physical processes that are taking place. And I think AI can be really, really helpful in helping advance understanding of the cascading impacts, just the events themselves. I think there's a lot of opportunities to help support the data fusion and coupling because you're dealing with a lot of truly disparate pieces of information, be it coming from the climate weather side or coming from the infrastructure system side. And it's not, and it takes a lot of effort and deliberation to think about truly how you start to couple that. I think as AI becomes more powerful and better at doing those types of things, it should help fill that gap very nicely to make it a little bit more seamless than it is now, which is a very, very ad hoc fashion. The other thing that I think is still a tremendous opportunity is thinking about uncertainty and a lot of these things. And we're starting to scratch the surface on how we're characterizing and quantifying uncertainty, and Pat's group has done a lot of fantastic work in that. And I think using AI can actually start to help that, especially as you're transitioning to the decision-making side of things, which is a whole other part that's got a lot of gaps as well.
All right. Thank you, Nicole. So these were the questions we prepared. So excuse me. I'm going to transition to the questions. We have about 5 minutes left. To the questions from the public, and I see a couple of questions here which I'm going to read next, but please feel free to write your questions. Okay, so the first question is for Andrea Castelletti. So you mentioned briefly talked about the fact that there's a lack of data as well, and what type of data have you noticed to be particularly absent, therefore requiring perhaps the use of generative AI?
Well, this two-dimensional reply. One is that gap are related to spatial heterogeneity of monitoring station. If we think about observational data, and this is somehow also conditioning the model we are developing, they're mostly available in the US, Europe, part of China now. So we're mostly using those data to calibrate model that then are, say, generalized overall the place. So this is one thing. The other thing, lack of data is related to the very nature of extreme events. So they are rare events, and so the number of occurrence of was mentioning before, hurricane of category 5 in the last 40 years is in the order of, I think, 100. So it means that not enough data to feed artificial intelligence tools.
Thank you, Andrea. The next question is for Nicole and Andrea as well. So Nicole, perhaps I'll start with you. What advances do you see where AI tools can better capture intelligence or state-aware adaptivity in the human systems that shape climate or sectoral systems, for example, energy, water, land, and agriculture?
Oh, that's a good question. I think actually sky's the limit as it comes to answering this question. I think there's a lot of potential, especially when you get to the reinforcement learning side of things and thinking about bringing together how your systems behave, what's the context of the system operating, and the human in the loop piece, and understanding how their decision making has impacted the system behavior, and then adding in the extra complexity of now you have, even though they are somewhat rare, these extreme weather events and perturbing the system as a whole. And so I think there's a lot that can be done, and it's kind of an exciting direction that I'm hoping to push my own research portfolio in, is thinking through how you can actually have more state-aware adaptation, especially as we start to think about on the grid side. There's a lot of questions surrounding how can owners and operators improve their mitigation portfolio, and having better tools to actually work through those exercises under lots and lots of scenarios is also a really exciting direction as well in the space.
Thank you, Nicole. Andrea, I don't know if you perhaps want to add something.
Yeah, I can add maybe just something related to yes, this human dimension, and again, like Nicole was mentioning, I see a lot of potential in reinforcement learning, in deep reinforcement learning, to also extract information from observational behavioral data. So in my group, we're doing some, just publish a paper actually. We're doing some experiment with these inverse reinforcement learning, which is a way that allow you to retrieve from a sequence of observational data the utility function or the utility functions which have driven the behavior that you see. So this is a way of extracting a model and then rebuild the optimization model that allow you to, for example, describe future behavior which somehow are consistent to observe the historical behavior. So I see a lot of potential also in that direction, which has nothing to do with extreme events.
Thank you, Andrea. So we have a little bit of time left in today's webinar. There are a few more questions, but unfortunately I will have to stop here with the questions. We have roughly 30 minutes left. I know that, so first of all, thanks again for joining, and I know that 90 minutes is a lot. But if you want to please stay online for another 30 minutes, 20 minutes or so, I'm going to now pass it to David Gold from the Utrecht University. He will go a little bit deeper together with Gillian Serteman later on what we're planning to achieve with this working group. And this is also a great opportunity to gather feedbacks from you. So Dave, please.
Thanks, Stefano. So hi, everyone. As Stefano said, I'm David Gold. I'm an assistant professor at Utrecht University, and I'm one of the co-chairs of the AI and MSD Working Group. And so I want to talk a little bit about our goals and our next steps for the working group, and also get some feedback from you all in terms of where we might go and what directions would be the most interesting. So first, to talk about the goals of the working group. So we have 4 main goals. The first is to review the current AI applications for MSD research. and provide a summary for the community. The second is to develop resources and trainings to help the MSD community utilize the tools that already exist. The third goal is to identify key research directions and priorities. And our final goal is to build and support an MSD community of folks who are working on AI issues with specific emphasis on building learning, networking, and collaboration across the community. So how are we going to do that? So the main kind of deliverable of our working group are these bi-monthly webinars. So this is the first of those. And you should be hearing from us every other month with different thematic webinars talking about AI issues and MSD science. The next working group deliverable is developing these resources and training. So we're still shaping exactly where we're going to be putting this, but this should be some code repositories and maybe some guides in terms of how you can get started out of the box with some of the existing AI tools and how you can apply it to your own research. Beyond that, we have an AGU session, so keep an eye out for that. It'll be AI and MSD research, so please apply if you are doing something that is applicable. And then finally, we're putting together a community publication that's summarizing kind of the state of the science and then identifying challenges and opportunities for AI and MSD research. So along that vein, we would love to get some input from everybody on this call and the community in general. We have 3 discussion questions, and we have some Google Docs that I believe Jillian is posting in the links or in the chat right now. So we'll start with the first one, and if you can either scan the QR code on the next slide or click on the link, and then Stefano, maybe you can, after people have a chance to load this, we can flip the screen to the Google Drive, and please log on to this or log into this discussion question sheet and add your answers here. So this first question is about what the dominant challenges and barriers are to advancing AI and MSD research, and then what also in everyone's view are the main opportunities that you see for AI. And if you feel comfortable, please add your name and your affiliation, and maybe we'll take about 5 minutes to start filling this out, and then we'll come back in 5 minutes and we can have a little bit of a discussion about where this is going and what everybody views as the challenges and barriers. So I'll let everybody fill this out. Again, I'll come back on in about 5 minutes.
And Dave, you can see my screen, right?
Yes, looking good.
Okay, perfect.
Okay, that was about 5 minutes, so feel free to keep responding if you're currently typing, but I'd like to take the time to kind of engage and make this a bit of an interactive discussion. So I'm going to just go through what's written here and maybe see if folks are comfortable sharing some of their thoughts. So the first one was from Jorge and kind of seconded from Nicole about data collection at fine temporal and spatial scales. Would either of you like to unmute, maybe turn your camera on and kind of elaborate on that? Oh, no, Jorge's no audio. So Nicole, if you're comfortable.
Oh, yes, happy to. So Jorge was the first to chime in about the data piece, but as it was kind of covered in all three of the talks today, there's differing levels of data that's available. And especially when you think about having a true an MSD style project, the data barrier can be quite significant. And as Jorge notes, it can occur across spatial and temporal scales. And then I also added in that especially from the MSD side of things, you can potentially end up with a huge mismatch of there's a lot of climate data, but maybe if you're thinking about infrastructure or different sectors within the infrastructure piece, sometimes you'll have not the same resolution if it's collected at all or if it's available to share. So the data piece is particularly a significant challenge.
Yeah, absolutely. So then moving on, I guess I'm going to skip down a little bit, but Rohini mentioned explainable AI and methods for explaining these complex multi-sector and interconnection systems. So Rohini, if you have the ability to unmute at the moment, I'd love to hear more about what you think about explainable AI.
Sure. Thanks, Dave. So yeah, I think there are a lot of great comments that built off of mine, but just thinking about how explainability is normally the barrier to adoption of a lot of ML AI models. And as we make these models expand multiple sectors, they just become increasingly more complex and nonlinear. And it kind of strikes me that a lot of the tools and methods that we're using for explainability tend to be more local, and so make assumptions about linearity, or you have to develop surrogate models, which may not represent the complexity. And so you then kind of wonder how much explainability you're actually getting. So I think that I'm just super interested in knowing what are the latest techniques out there. How would you even partition some of these larger models to do these types of sensitivity or explainability analyses? So yeah, so I think that's a cool area, and I'd be really excited to know what work is going on in that space.
Fantastic. Thanks, Rohini. For the sake of time, I think I'm going to jump to the opportunities. So if we scroll down a little bit, not quite discussion question 2 yet. So I wanted to maybe call on Jared, who mentioned creating multi-sector models using physical structures, which I think ties into this discussion so far quite nicely with an example of filling gaps in interbasin transfer locations. So Jared, if you're on and you'd be up for speaking, please feel free to turn your camera on and unmute.
I don't know if I have more to say than what you had already narrated there, but I think the idea is that we could probably learn ways to infer operations, especially operations that we don't have data on. And maybe that involves looking at residuals, maybe it involves something like Xiaopeng has mentioned in differential modeling, and how to integrate components that we know and components that we don't know into the system. So I think there's a lot of opportunity here.
Excellent. Thanks, Jared. I completely agree. So we'll do one more and then we'll switch to the next discussion. So Orlando Roman, if you're on, I see your comment on AI can enable the use of computationally expensive models, agent-based models on transportation, for example. So yeah, if you care to elaborate on that a little bit, I think that would be a great area for us to go into for the conversation.
Yeah, thank you. Can you hear me well?
Yes.
So yeah, I work mainly on the land use, transport, interactions field, and we use a lot of agent-based models because when we talk about transportation, there's a lot of research about behavioral models, choice models, so how people make decisions in cities, how they pick different transport modes and different ways of housing, etc. So these models are people like them. They are very computationally expensive. They take a day to run. They are very detailed, spatially explicit, but they are so complicated that it's difficult to use them when considering uncertainty, for example, when running several scenarios. So we are using AI to try to enable the use of these type of models for decision making under uncertainty by fitting or developing surrogate models, so fast approximations of these complex models, or using Bayesian optimization, for example, to enable the optimization of these systems with these very complex models. So I think that's an area of research that can be exploited because it explored more. There's not a lot of people that I see working on these type of models and using AI to use them for decision making.
Well, thank you, Orlando. For the sake of time, I think we have to pivot to question 2, with which Jillian just posted in the chat. So for this one, we're interested in hearing what everyone thinks are specific domains of applications that you would like to see highlighted in the next working group event. So as we mentioned earlier, we have a number of webinars. We're going to be doing these bi-monthly. We're also putting together resources. So this is an opportunity to tell us what you would like to see in our upcoming webinars and in our resources. And we'll be using this feedback to directly shape our next set of events. So again, we'll take about 5 minutes to have everybody answer this discussion question, and then we'll come back and recap what everybody's thinking. Right, we're coming right up to 5 minutes. I'm gonna list some of these. I think for the sake of time, we'll transition to the next question because I want to make sure we can get folks' feedback on that. But some of the ideas I see listed here are thinking about the multi-sectoral applications that bridge different domains, as suggested by Pat. From Jill, the various machine learning and artificial intelligence models used across the MSD community. From Stefano, modeling human decisions with AI tools, which I also think is a really interesting application. And so thanks everyone for making these suggestions. The last discussion question and the last feedback we'd like to hear from everyone, and that Jill just posted in the chat, concerns emerging analytical approaches in artificial intelligence that you would like to see, that you would like to see highlighted in our training sessions. And also, if you could list any resources, for example, data sets, GitHub repositories, that you think are relevant and could be of use to the broader MSD community in applying AI for MSD research. So again, we'll take some time to fill this out, and then we'll come back and review, and we'll wrap up. I'd also like to note that Jill, a little while ago, posted in the chat the link if you'd like to join our working group or the MSD community in general. So we'll post that again towards the end of the webinar, but just a reminder before everybody takes off. All right, so we have about 5 minutes left, so I'll bring it back. So thanks everyone for your feedback and your comments. Just to review again, and maybe we can open this up a little bit more. So thinking about reinforcement learning based toolkits, as Pat suggests, for stochastic approaches and deep learning extensions. And then Angelo mentions that there are many libraries to implement these, but developing a simple environment would be useful. I completely agree. And thanks, Angelo, for posting that resource there. Stefano talks about generative AI to create spatially distributed data sets of extreme weather events, and maybe using LLMs. And Don, I like the suggestion of using large language models as a medium to help communicate or translate this information. I think that ties into some comments that we've seen. I think there was one from Jasmine about explainable AI tools and competencies necessary to use AI. Thanks for posting that Gym link, Jasmine. Jared also posts knowledge guided approaches and a review paper there. And let's see, we have, I guess, another paper right below that. And we have UG posting AI tools on satellite data processing, large language models, generating simulations, or creating surrogates. So I think these are all great directions, and we'll definitely be taking them into account. We have about 4 minutes left, so I guess I would first like to say let's thank our speakers one more time. I think those were great talks today. And I'd also like to remind you that you can join us on the MSD website. I'll repost the link here, or it might have just gotten posted. Yeah, thank you, Jill. And if anybody has anything else that they'd like to say, before we hop off, we have a couple minutes for closing remarks. Otherwise, thank you very much for coming, and we look forward to seeing you at the next AI and MSD Working Group webinar event, which should come late summer, early fall.
Thank you.
Thanks, Dave and Steph.